Okay, we are recording. All right, so we're talking about section 4.3, derivative inverse trig functions. So let's start with derivative inverse sine. Now, hopefully you guys remember what inverse sine is all about. Let me give you guys a little bit of a quick recap from pre-calculus from last year. And I'm very, very glad we did trig in the fall, because I can imagine you guys trying to learn trig in our remote plan last spring. So if I draw a right triangle off to the right here, here's a right triangle. We'll call this theta. Actually, let me call this y. We'll call this y. And what would sine y be? Well, sine of an angle is always going to be opposite over hypotenuse. We know this, right? You guys should be familiar with SOHCAHTOA. So say, for example, this I call the side x, and I call the side 1. Well, what's sine y going to equal? X over 1, right? So sine y equals x over 1. Or sine y just equals plain old x. Well, how would you isolate y? You would isolate y by doing this, inverse sine. So remember, an inverse sine, it's reversed, right? So traditionally, we had sine theta equal opposite of hypotenuse. Traditionally, the input was an angle measure, right? We know this. And the output was a ratio of two sides of a right triangle. Again, all stuff we know. You don't want to write this down, you don't have to. If it's all just, okay, blah, 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 okay, Mr. I get this, fine, but I just have to talk about it. So output is a ratio of two. So that was for a regular trig function. For the inverse, it's reversed, right? So now this, the input, is now a ratio of two sides. Remember, I called these sides to the opposite x, hypotenuse 1, ratio x over 1, opposite of hypotenuse. And the output is now an angle measure. Excuse me. Is now an angle measure. So that's something we just have to make sure we're very clear about. So in this case, if y equals inverse sine of x, well, then x equals sine y. Hope that makes sense. So like, for example, like if I do inverse sine of 1/2, you guys might remember this from a while ago, that's going to be pi over 6, because sine of pi over 6 is 1/2. That's straight from the unit circle, right? Where pi over 6 is an angle in radians, 1/2 is a ratio of two sides. In fact, it's the short leg and the hypotenuse from a 36-90 right triangle. So, we know that these are interchangeable. Inverse sine 1/2 is pi over 6, or sine pi over 6 1/2. They're basically the same thing, just another way of writing it. You're switching the input and output because it's an inverse. All right, so now that we're clear about that, let's actually take the derivative of it. Let's do it. So let me clear some of the stuff here. Okay, so I'm not sure why there's an and here. I don't know why that's there, but let me just cross that off. So again, that's the same thing, x equals sine y. Well, if you do implicit differentiation, I hope you guys remember that. Hope you guys didn't forget our break. You take the derivative both sides with respect to x. And that's going to be 1. And would someone like to tell me what's the right side going to be? Or you could type in the chat. You guys remember derivative sign?
It's cosine, right?
Good. Thank you. Thank you, Connor. However, you got to do times dy over dx. The reason why is because you have a y there, right? And then you isolate dy over dx, which is that. Great. So that's the derivative of inverse sine of x. It's 1 over cosine y. Now, that does seem a bit weird. And just work with, just stay with me here. I'm going to do more stuff with this in just a little bit. But before I do more stuff with it, one thing you have to be a little bit mindful about. The graph of inverse sine of x is shown down below. Maybe you guys did that in pre-calculus, I don't know. But when you take when you do the inverse sine of x, you have a default range. So the default range is this. So if you were to actually do inverse sine in your calculator, you see the inverse sine of like something really funky, like I don't know, say like 3/5. Then it's going to give you an angle that's between negative pi over 2 and pi over 2 in radians. By the way, we're always going to stick with radians. We're never using degrees here. That's also very important too. Make sure your calculator stays in radian mode. The reason why is based upon the derivation of the derivative of trig functions. We assumed radians. We did that a couple weeks ago. So yeah, always use radians. So that's the default range. Now, another thing you have to be mindful about too is that there's a restricted domain as well. What if I try to do an inverse sine of like 7/2? Why would that be bad? Like, why would the calculator give me an error if I tried doing that?
Because it's not a value on the unit circle.
Yes, and also the fact that sine is opposite of hypotenuse. Can the opposite side be 7 and hypotenuse be 2? Can the opposite be bigger than the hypotenuse? No. No, the hypotenuse is always the biggest side of a right triangle. So that's impossible. So the domain is always restricted between -1 and 1 for inverse sine. Likewise for inverse cosine. And now this is actually a graph that repeats. The graph actually looks like this. It repeats going up and down the y-axis. But you have a restricted range from negative pi over 2 to pi over 2 because you want to pass the vertical line test. You want the inverse sine to be a function. Remember, to be a function, for every input is only one output. So that's why we have a default range, in case you guys forgot. And that's why the calculator only spits out anything from negative pi over 2 to pi over 2. So just some of the things we need to keep in mind as well with our derivative of inverse trig functions. Now, great. dy over dx is 1 over cosine y. Awesome. Okay. Well, here's what we should do, because we still want this in terms of x, right? We want to get this in terms of x. So I'm going to clear my drawings and scroll down. I'm not sure how you'd use a Pythagorean identity to get the derivative in terms of x. So I'm going to do something a little different. I'm going to cross it off. The way I'm going to do it is actually going to be, it's kind of similar, but I like to take this approach instead. So let me redraw that triangle that I did just a few minutes ago. So remember, this was y, this is x, this is 1. And remember, we're dealing with y equals inverse sine of x. And when I took the derivative, when I then rewrote it like this, x equals sine y. And when I found the derivative, remember I did all this work at 1 over cosine y. Now, let's take a look at this right triangle here. I'll call this side A here. What would A equal in terms of x? How would I do that? Does anyone see what A equals here?
1 minus x squared.
Yeah, the square root. Right. Good. Thank you. that doesn't look good. I can do better than that. Okay, well, what's cosine of y going to be here? Is that just going to be adjacent over hypotenuse? And what's my adjacent? Root 1 minus x squared. What's my hypotenuse? 1. So that's cosine. So dy over dx can now be rewritten as 1 over root 1 minus x squared. And that's how we actually express the derivative of inverse sine. 1 over root 1 minus x squared. It seems really weird, and a lot of times some students are just told the formula, like maybe some calculus classes that don't really go into theory so much, or people just don't really are not fully engaged. They kind of say, well, that's just what it is, and you just use it. But I want to make sure you understand why. Why is it root 1 minus x squared? That's because we started with this, and we learned last year that that means this. And if you treat y as an angle, because that's what we do for traditional trig functions, and treat x as a ratio of 2 sides, or x over 1, well, yeah, of course sine y equals x over 1. We draw this right triangle here. And then if I use Pythagorean theorem to solve for the other leg, which I got root 1 minus x squared, that gave the cosine. And when I took the derivative of x equals sine y by implicit means, I got 1 over cosine y, but cosine y, of course, is just root 1 minus x squared. So the answer is 1 over. So that's kind of the chain of events that happen here. So the derivative of this is 1 over root 1 minus x squared. Now, technically, our side here could be negative. So technically, it's plus or minus. But what we're doing here is that we had a default range, right? Remember, for inverse sine, our default range was negative pi over 2 to pi over 2. So our right triangle is going to look like this, or it could look like this. But bottom line is that the horizontal leg is positive, just given the nature of what we're working with here. So, and plus our graph of x, you look at the graph of inverse sine of x, right? Which was right above. The graph of inverse sine of x look like this, right? If you do tangent lines here, would your tangent lines on this graph of inverse sine of x, would the tangent lines here be positive or negative? What do you guys think? Positive, right? Positive. So that's why you got to maintain that this stays as a positive output for derivative inverse sine, that the slopes of the tangent lines are always positive. Of course it'll be, because you have 1 is positive, and the square root of something is going to come out as being positive, unless you put a negative outside the square, but we don't put a negative out there, because we got to maintain that stays positive. So dy over dx will be greater than 0, because 1 over cosine y is greater than 0. Remember Q4? Remember all sine, tan, cosine. So cosine just stays positive, whether you're in Q1 or Q4, because that's our default range. Now, there's a chain rule that you can do with this too. Before I get into that, one just little quick thing I need to let you guys know is that, remember this little cheat sheet that I told you guys about? And there are a lot of things that are helpful, like product rule, quotient rule, chain rule, implicit differentiation. We didn't cover inverse trig stuff. And I mean, in our last unit, we are now, obviously. It has all the stuff here, all the inverse trig stuff, all the derivatives, all right here. They look really wacky. Don't let it freak you out. I'm going to show you how they're all derived within the hour. And then on Thursday, we're going to do derivative exponential log functions. So remember exponential logs. We're going to do a crash course on it on Thursday. Have a worksheet to help you with that. And then we'll do derivatives with that as well. Anyway, but I want to make sure you guys saw that the cheat sheet has those as well. All right, so we may have to do a chain rule with inverse trig functions. So u here is some function in terms of x. So So you still do the same thing. You do 1 over root 1 minus u squared. So whatever u is, whatever thing you got in terms of x, square that, right? But times d over dx. Remember, the times d over the outside, right? We want to do that. So let's take a look at example 1 now. So you got derivative inverse sine of 7x plus x cubed. This is your inside, right? We know this. So if this jogs your memory, what we did in our last unit, we did a lot of chain rule stuff, right? So it's going to be 1 over root 1 minus something squared times something. What's my inside here? Obviously, it's 7x plus x cubed, so keep it intact. And multiply by the derivative of the inside. Well, what's the derivative of my inside? That's easy. That's just 7 plus 3x squared. So final answer is 1 over root 1 minus 7x plus x cubed squared times 7 plus 3x squared. So there we go. That is going to be our final answer. Looks a little weird, I know, but just want to make sure we understand what we're doing. Now you could check your work if you like. I'm going to pull up the TI A4 calculator, and I'll get back to the solution in just a second if you're still copying it down. Okay. And it's probably going to tell me I got to buy a subscription. Or if I have like a few days left. Oh, I have 14 days. Okay, that's perfect because that's when we have our next test. So, but I'll obviously have to take care of that soon. No, I don't want to. Just give me the trial version. Okay, just wait for it to open up. And let me actually minimize this. Okay. Yeah, so anyway, go to y equals. So it was inverse sine. Let me go and clear the screen right now. Inverse sine of 7x plus x cubed. And y2, I take derivative of y with x equals x. What I got by hand was, I'll do parentheses, 1 over parentheses, square roots. It's going to be really not kind of nasty, right? 1 minus, remember I kept the inside intact, 7x plus x cubed squared, and my parentheses, and then that was times 7 plus 3x squared. Make sure I did all that correctly. Yeah, all looks good to me. And I'll turn off the first one. I'm going to make sure I'm in radian mode. I'll graph in the Z trig window. And I see nothing. Why not? Let me zoom out. Or hold on, Z trig. There we go. No? Let's go standard. Okay. Let's zoom out again. Okay, don't understand why I'm not seeing anything here. Maybe I have to make it tighter. Actually, I'm not sure I did 1 point. It should be 0.5 pi. Okay, if I can't figure it out, then just trust me, I did this right. Let me try this one more time. Let's go negative 50 and 50. Okay, I feel a little better now about that. So I hit trace. You can see I'm on Y2. If I hit the down key, for Y3, I'm still on the same curve. So I know I've done this right. Okay. Let me undo my erasings. So any questions about example 1? No? Okay. So now that, go ahead. Yeah.
This might be a stupid question, but in the graph of inverse sine, it was kind of like an S curve, and then it was like a U. Why did the left-hand side flip up?
I don't know. Not sure. Don't know. I mean, it could be, the fact that everything stays positive because you have a square root, maybe, I don't know, but you have 7 plus 3x squared, which also stays positive. I wouldn't worry too much about that. But you just want to make sure you did it correctly. That is just a verification process. So yeah, no need to overthink that. Okay, now let's do inverse tan. Now, inverse tan has the same default range. In fact, the graph of inverse tan is off to the right. And remember what this means, that x equals tangent y. Just like how inverse y equals inverse sine of x, then x equals sine y. So it's the same thing here. I'm not sure why there's an and here. I'm just going to get rid of that. And if you draw tangent lines to inverse tan, like if you actually graph inverse tan in your calculator or in Desmos, and we're in radian mode, and just the domain, you could do anything. Remember, tangent is of opposite of adjacent. Opposite adjacent sides could be really anything. So you could have it be infinite or whatever. So for y equals tangent x, this is y equals tangent x. Remember that there are asymptotes here. So the range was all real numbers, but the domain was restricted. So you kind of see things reversed here. But now the domain is all real numbers for inverse tan, and the range is restricted. And we do have a default range from negative pi over 2 to pi over 2 because the graph actually would repeat itself like this and would fail the vertical line test. So you have to restrict the range to avoid a failure of the vertical line test. Anyway, let's do the implicit differentiation. So let's take both sides back to x just like we did in the previous page. So that's going to be 1 equals, now that's secant squared y. Hope you guys remember that. But times dy over dx. So dy over dx will then be 1 over secant squared y. And give me 1 sec here. Something else I'm kind of blanking on. Hold on 1 sec. No, we're good. So let's keep moving. So that's what's going on there, right? Now, you could, if you want, and let's actually draw this too. So tangent y equals x. Means this. Right triangle, here's y, and that's like saying x over 1. So that's x, and now that's 1. So let's solve for our hypotenuse. So it's a different right triangle than the previous page. 1 squared plus x squared equals c squared. So your hypotenuse is just root 1 plus x squared. Okay. Now, to get the derivative in terms of x, you could do this. You could go about this a few ways. Secant squared we know is 1 over cosine squared. So dy over dx is cosine squared y, right? Because secant squared is 1 over cosine. I mean, secant is 1 over cosine, so you flip it. And cosine here, of course, is 1 over c, or cosine y is 1 over root 1 plus x squared. But since you're squaring it, it's 1 over 1 plus x squared. So that's the derivative of inverse tan. It's just 1 over 1 plus x squared. And that should always stay positive. You see here, we have a bunch of positive tangent lines, so it should always stay positive. So it's 1 over 1 plus x squared. And so it's always positive because our tangent lines from the graph are always positive. And if you do a chain rule, you should have 1 over 1 plus u squared but times d over dx. Okay, so that's another formula we have, and let's actually apply it. And let's just ignore this question. I don't care about that question right now. So let's take the derivative of this guy here. So that's just going to be 1 over 1 plus something squared times the derivative of something. What's my inside? Sine x. Remember, keep that intact. So sine x here. And you take derivative of sine x. So final answer is going to be cosine x over 1 plus sine squared x. That would represent the derivative of that example right there. Again, you can use Desmos, not Desmos, sorry, the TI-84 calculator to check your work. Where you, under y1, you put the original function, y2, you do d dx of y1, vertical line x equals x. y3, of course, whatever you get by hand, you put under y3. And yet we have another one. We have also the inverse secant. Excuse me. We have inverse secant. And a secant graph looks like this. Sorry, inverse secant graph looks like that. It's a little strange. I'm not going to get into it too much. But anyway, that derivative, I'm just going to kind of tell you what it is. You could do the same kind of thing we've done before, but it looks like this. Absolute of x times 1 minus x squared. I mean, we are dealing with inverse secant, just so you know, inverse secant of x equals y. So secant y equals x. And if you were to draw a triangle, you know, here's y, but then it's secant, so that's x and that's 1. So it's reversed. So therefore, this is root 1 minus x squared And you could go through the whole motions if you wanted to, like, okay, let me take the implicit differentiation here. I'll do it kind of quickly. It's secant y times tan y times dy over dx equals 1. Anyway, I'm not going to get into it in the interest of time. Just trust me, it works. This is the derivative. And again, your formula sheet. Oh, shoot, I did reverse it. Darn it. I should have done the derivation. Sorry, my bad. It's x squared minus 1. Okay, that's why we have the formula sheet. I should have done the derivation. My apologies. Yeah, that's because if I do the Pythagorean theorem correctly here, actually it was root x squared minus 1. My bad. Anyway, just trust me, that's what it is. And if you do a chain rule, it'd be 1 over the absolute value of u times square of u squared minus 1, but then times d over dx. Again, so it's always positive, so that's when we have the absolute value around dx. And of course, squaring x squared minus 1. And there is a domain here that we have to stick to, which is that. Again, I'm not going to get into all the semantics there, but remember, when you are dealing with like y equals secant x, right? That's 1 over cosine x. Your range is definitely going to be higher than 1 or less than -1. Whereas for cosine, the range is always between -1 and 1. We know the lowest point is -1, highest point is +1. Secant does like this kind of stuff down here. It had always like U shapes. You might remember that from a while ago. So it has a different range. And when you're in the inverse, the range for the original becomes a domain for the inverse. That's why that domain's right there. And it would also ensure that you're doing this correctly because you can't square at negative numbers. So yeah, it does matter to know that, but for the derivative itself, you're fine. So that's another formula. Again, for our next test, you don't have to memorize. You can just use your cheat sheet. On the AP exam, if somehow the AP exam goes back to normal, highly doubt it will. I'd be surprised. So most likely be online, then great, just do it from home. They did it last year just fine online. Just do that and just have your formula sheet. But if it's in person, you'd have to memorize it. But I don't think it's too bad because we do enough practice in the spring, you start memorizing all these things. Then let's talk about inverse cosine, inverse cotan, inverse cosecant, and then we'll do a few examples here. And at that point, I'll probably have to stop the video, stop our lesson because I don't think I want to quite get into that today, which means I'm going to have to make a video on this and have you guys watch it. That's fine. That's not a big deal. I can totally do that. But let's talk about these bad boys here. Excuse me. So what about inverse cosine, inverse cotan, inverse cosecant? Well, let me kind of give you the formulas right now and explain why they are the way they are. This will be -1 over root 1 minus x squared. This will be -1 over 1 plus x squared. This will be -1 over absolute of x times square of x squared minus 1. So you'll notice that they're simply just the negative counterparts of their complement trig functions. So inverse cosine is just a negative counterpart of sine. Inverse derivative of inverse cotan is a negative counterpart of, or it's just a negative of inverse tan, the derivative of inverse tan. And likewise for inverse cosecant to secant. And maybe you guys don't remember this or don't realize it, but sine and cosine, the CO is actually an abbreviation of complement. You might remember complement angles from geometry many years ago. Complement angles are two angles after 90 degrees, right? And so and that's likewise for secant, cosecant, tan, cotan. So there are these things called cofunction identities. Let's say I call this alpha, and say I call this like beta. So I'll put alpha here and beta here. So if alpha equals inverse sine of x, then of course x equals sine alpha. Wait, sorry, I messed that one up really hard. My bad. Let me backtrack. That was terrible. I just did. Yes, this is an angle. I wasn't mistaken about that. That's an angle too. Let me just start with alpha first. So here's alpha, and so that's x, and that's 1, and that's beta. Okay, actually, I wasn't totally wrong what I did. And that's beta. Well, wouldn't alpha plus beta add up to 90 degrees? Right? Those are complements. Sine of alpha is x over 1. Cosine of beta is adjacent over hypotenuse. That's x, also x over 1. So anyway, if sine alpha equals x over 1, then alpha is the inverse sine of x. If cosine beta, now I know what I was doing wrong. I was doing this out of order. Cosine beta is x over 1. So wouldn't beta be inverse cosine of x, right? And of course, alpha plus beta equals 90 degrees. Well, if you isolate inverse cosine, then you'd have pi over 2 minus inverse sine of x. Now take the derivative of both sides here. d dx of pi over 2 minus inverse sine of x. Well, what's the derivative of pi over 2? That's a constant. That's 0. What's the derivative of inverse sine? We know that from the first page. 1 over root 1 minus x squared. Hence, the derivative of inverse cosine is negative 1 over root 1 minus x squared. And if you do the same thing for inverse cotan or inverse cosecant, you'll get the same thing. And off to the right is what I did off to the left. I don't know why I did my own thing. I could have just done what was here in the box. Yeah, sine alpha, of course, is 3/5. Cosine beta is also 3/5. Alpha plus beta has to have to 90 degrees, or pi over 2. So hence, the inverse sine of 3/5 plus inverse cosine of 3/5 must equal pi over 2. So that kind of illustrates these cofunction identities, why they work the way they do. So those are more formulas. Again, they're on the cheat sheet. Now we have to apply them. So we'll do examples 3, 4, 5, and then I think we'll stop class there because that's a lot to do. So example 3. And remember what rule I have to use here?
Product.
Very good. Product rule. So your derivative is going to be the derivative x, which is 1, times inverse cos of x, plus x times derivative of the inverse cosine. Now, we already know what it is. We have the formula. So there you go. Just use the formula at this point. You don't have to keep going through the how the formula came about. And that's just going to be x times negative 1 over root 1 minus x squared. And just leave it like that. Do not simplify. Just leave it like that. It's totally fine. And again, you can use your type 4 calculator to verify your work. Okay. Let's look at example 4. You're asked to find a normal line. Remember, that's perpendicular to tangent line. And arctan, arctan's kind of a weird way of writing it. It's no different than just saying this. I don't remember the history, like why that was popular, but arctan just means inverse tan, just so you know. Don't freak out over that. Anyway, let's take our derivative. dy over dx will equal 1 over, now it's inverse tan, so you gotta do 1 plus something squared times the derivative of something. What's that something? Root x, right, because that's your inside. So all these things that we've done before, they all get reinforced. So don't worry if you forgot stuff, because guess what? You're gonna be forced to remember it as we're going through all this stuff here. You have 1 over 1 plus x, just 1 over 1 plus x. Derivative of that's gonna be 1/2 times x and negative 1/2. Or 1 over 2 root x. It's kind of good just to know that right off the bat. Well, we're not done yet. That's our derivative. But yeah, remember root x is saying x to the half. And you move the 1/2 to the front and draws the exponent by 1, which is the same thing as saying 1 over 2 root x. We know this, okay? We're good. Well, what's the slope of the tangent line? Easy peasy, that's just going to be 1 over 1 plus 4 times 1 over 2 root 4. So 1/5 times 1/4. Or 1/20. However, what will be my perpendicular slope? -20, right? Because you got to do negative reciprocal. And just make sure I did all that correctly. Yeah. So your normal line is going to be y minus something times -20 times x minus 4. So we got to do the inverse tan to figure out what that is. Let me do that off to the side here. That's not something you can do in your head, just so you know. You'll need to use one of these guys. Make sure you're in radian mode, very important. You get 1.107. So that's what I'll put right here. Y minus 1.107 equals -20 x minus 4. And you can actually check your work. You could just graph this in Desmos, graph your normal line, and it should look like the touch on x equals 4 and that it's perpendicular to whatever tangent line you would have there. So you can always use Desmos to check your work too. Okay, Catherine, go ahead.
If you were given like y equals 4 instead of x equals 4, how would you solve for x to write the equation?
You replace y with 4, obviously, and then you'd have to then undo the inverse tan by doing, so you have 4 equals inverse tan of root x. Then you would say tan 4 equals root x. And then, of course, solve for x out. But rarely is that ever asked. Typically, you're asked, like, at a certain x value, find me a tangent normal line. It's rare that you be given the y coordinate first. Usually, you're given the x coordinate. I've never really seen that. But yeah, that's what you would do. So it's all the same kind of skills as before, nothing different. This will be our last example, and we'll stop there. And then I'll have to make a video on pages 5 and 6. So basically, the homework I'll update. There'll be a video on pages 5 and 6, and there'll be a worksheet. And actually, I'll probably I'm trying to think here. I'll probably remove the worksheet because I think it might be a little much. Instead, I'll just keep text. So I'll do video and homework problems. So I'll make an update to that. The worksheets, then we'll just save that for Thursday. Because there's some works on inverse trig stuff. Sorry, on inverse functions in general. It might be a little hard to do after the video. I'll save that for class on Thursday. So don't start the homework just yet. After we finish class, I'll maybe make an update to it with the video and just textbook problems. Anyway, let's look at example 5. So we're the last one for today. So S, same thing as Y. It's it's all arbitrary. It doesn't really matter. So dSdt is -1. Remember, it's -1 over root 1 minus something squared times something derivative. What's my something? Right there. That's my inside. Let's put t over 4 and t over 4. So then I get this. And let me make that more neat. Okay. Personally, I'm fine if you leave it that way. However, on an AP exam, they will probably write the answer a little differently than that. They'll actually do some simplification. And that's kind of what is the whole point of this problem. How do you actually simplify? The calculus is easy. I have no qualms if you guys understand the calculus. I think you guys will be fine at that. It's the fractions, believe it or not, that's actually the challenge. So what you do if you simplify it is you write this as 16 over 16 minus t squared over 16. And that's times 1/4. So 16 minus t squared over 16. So again, I changed 1 to 16 over 16, find LCD, combine it. Didn't leave myself enough room. That's okay. So it's, then you could write it as -1 over root 16 minus t squared over 16. Sorry, over 4. Yikes, because it's square rooted. And you still have times 1 over 4. Now, what you could do is you could flip this over, or you could just see that there's obviously crosses off right like that. So the answer would be -1 over root 16 minus t squared. And that's probably how you would see the answer look in one of the choices on a multiple choice exam, AP exam. So see, you would have this, but then you'd see this as the choice and you're not sure if you're doing it correctly, right? So that's why you have to be mindful about simplifying sometimes. It's not hard, you just have to remember your fraction with it and be careful. But that's how you would simplify the answer. Or the textbook, sometimes they put answers like that too. So you just have to be, I just want to kind of show you that process of going through the simplification. Okay, I think that pretty much covers as far as I want to get to today. Actually, I'm kind of glad I didn't get to pages 5 and 6 because I think I've been a little too overwhelming. So I think I'll put that as a video. It's a little tricky, a little confusing, but it's okay. I'll have to try some textbook problems on it, and then we'll do some worksheets on the derivative inverse functions in general. on Thursday. And then we'll do a video, then a lesson on 4.4. 4.4 is actually pretty quick. It's actually one of the easier sections that we do. Let me just take a quick peek of that. So I'm not out to lunch thinking I could do all this on Monday. I think we'll be okay. Well, we shall see. It's very mechanical, so I'm confident I could get to all this. Okay, anyway, that pretty much covers it. For any questions, feel free to stay behind. We'll end class a couple minutes early. Again, hold off on doing homework. I do need to make a. I'm probably gonna squeeze it in right now because I could do a really short video on pages 5 and 6 of the section 4.3 notes, and I'll update Schoology. By lunchtime, it should be all set if you want to get ahead start homework. So again, we'll do this again on Thursday. Hopefully, I feel better. Hopefully, I get a negative COVID test so I can finally leave the house. So we shall see. And be careful out there. It's definitely it's really easy to get sick now. Even if it's just a normal cold, whatever I had, it was horrible. So I don't wish that on anybody. All right, I'll see you guys later.
Thank you.
Thank you, Mr. Reed.
Thank you.
Thank you, Mr. Reed.